Okay, start recording. Welcome everyone to this new episode of EagleFly, the experimental debugger. Today is a new day, and we will continue reading about the IA32 architecture. I believe we have now a good set of recordings about IA32. It's been such a pleasant thing to do. As I always say, looking at the real stuff going on behind the computer, inside the processor, it's gonna clear the mind. It's a mind clearer, and that's what we want. We want to understand the last bit of processing capacity that our current processor can handle. And fellas, this is not an easy task. And we've been doing great. We've been reading about the architecture itself, how these registers hold on data inside, how does they encode data inside those registers as different numeric types. We know how they manage exceptions for floating point instructions. We also know how does the control flags sometimes they get used by some operations, and that's pretty much basic. We are just about entering into the real stuff. Well, I guess everything is real, but we're gonna enter, if I believe so. Let me open the IA. And yeah, this is it. This is the next thing that we will take a look on, and it's basically the instruction set summary. This is not the whole set. This is just the summary itself. If we want to go into the details, we will need to read each one specifically. And I believe we can start by looking at them in a more general sense. Okay, what does they do? Where can we use it? How can we use it? And it's something like that. So I think that we should start. Okay, please, if you have any questions, feel free to ask them after the stream has ended. I'll be there to answer them, and yeah, with that in mind, I think I will continue. And yeah, you can post your questions on Twitter, Twitch, or YouTube. So yeah, I can watch them later there. So yeah, okay. So let's dive into the instruction set summary for the IA32 and 64 processing architectures. Okay, so this is interesting. These are the processors themselves that can process x87 FPU. I mean, the general purpose registers can be used by any processor, Intel 64 and IF82 processors. SC4.1 extensions. Use CPU ID to verify presence of ASNI ASNI I don't know how do you pronounce it. AESNI MPCL MULQDQ across intercross processor families. They have, yeah, we need to get to see that's inside this processor. Intel Xeon processor E3 and E5 families. And I mean we're not gonna use most of these instructions just because I mean if you see, I mean they are sometimes, I mean especially the ones that are really specific to certain platforms, it's not like they don't generalize good to the thing that we probably want to do, you know. So I mean we want to keep mostly to the instruction set architecture that most of the computers and processors can handle, you know. In so yeah, I mean it would be really nice to use all these kind of instructions if we can, of course, but I mean we can use them, but the user itself debugging cannot, so it's gonna be some kind of caveat there, you know. For example, ASNI and PCMO QDQ. I don't know if you have them. Probably not, but we can check with the CPU ID. For AVX, the Xeon processor E3 and E5 families, a second generation Intel Core i7, i5, and i3 processor 2X families. I guess that yeah. F166 and RDRAM FSGS base access. You get it on the third generation of Intel Core processors and Intel Xeon processor E3 or 1300 B2 product. So if you think about it, it's kind of interesting how does the compiler itself handle uh, to write instructions this way, you know. because I mean the compiler has, well, not necessarily of course, but but uh, going deeper into compiler stuff and assembler stuff, the compiler has to have some kind of notion of what kind of instructions he can set on different architectures, and it's it's kind of interesting. It's always good and safe to like stick to the most common architecture instructions. But yeah, I mean, it all depends on. I don't think they do SIMD at all. I don't. I don't know. I mean, probably they don't. I mean, following the idea of how does they. Yeah, I mean, they have to stick with really basic instructions, like general purpose and x87 FPU and probably MMX, but I don't think so. They use MMX. Who knows? But I mean, going to SSC, it's like it can be a little bit of a caveat there, and you don't know if the processor itself is gonna handle those instructions, and yeah, I mean, it's I don't think the compilers use SSC instructions at all, but who knows? So as well as I mean, looking at the debugger probably doesn't, but here's the caveat. A debugger, I mean, one thing is that the compiler doesn't generate those instructions, but the user can trivially insert those instructions, and that's the kind of, I mean, the user can put any instructions if the processor handles them, and the debugger itself is gonna read those instructions, It's gonna take a look at, at this line of the instruction pointer, we have an SSC2 instruction running on, and it's a kind of funny thing, because it's like, oh, okay, so it's, I mean, now, I mean, it's all about how the user uses and exploits these processor architecture, So it's not like a. So that's the difference between what the debugger should and at least understand. I mean, probably. I mean, we can say like, for example, for basic stuff, that we cannot read same instructions, but I don't think it's gonna be. It's a kind of a tricky question, isn't it? I mean, which way to go? I mean, we can go deep and straight deep into the processor architecture, being parsing out all the instructions and understanding the whole set architecture, so that we can handle specifically one architecture or two architectures, or let's say that we focus on the IFA2 architecture, IFA2 and 64 architecture, so we can handle all in a deeper manner all these things, that instead of going wider and think about multiple, not just, I mean, because think about it, I mean, if you, I mean, look at the wider picture. I mean, we can look at the deeper picture. They can go like, oh, let's parse the whole IFA2 architecture and see the whole instruction set, we can go that route, or we can go the other route. They could be like, hey, we don't care too much about deeper things, but we care much about operating system compatibility, because that's also an important thing. Okay, so if the debugger wants to have multi-platform and now by platform, I mean like multi-operating system targets, so then we have like this extra complexity there, like, oh, I want to process not only these platforms but also these operating systems, so it's a kind of it's a kind of another combination there that you have to handle, and that's basically, I mean, it depends on how do you want to go. If you want to go deeper then it's a kind of it's gonna take more time, of course. It's gonna take more time to handle each one specifically. Each platform and each operating system. So it's a tricky thing. It's a tricky thing, but um, we have to answer that question as we go, I guess, because I mean, also part of this debugger thing that I'm doing right here is uh, it's not just. I mean, of course, I want something that it's usable, of course, but I also want to dig a little bit deep, in the things that we are doing here because I don't think. I mean, and it's all part of this low level stuff that I mean I always and as I'm a hero, like all these ideas and mindsets about okay how to handle this stuff. I mean, trying to understand more about how something it's something that stakes. I mean, it's something that goes beyond just this process of this project, and sticks for the whole thing, for your whole life. If you go deep, you go. I mean, you go deep, you go deep, man. You know what I mean? If you go deep, you will stick that forever. If you go deep, everything that you go and see basically gets more sense. Because if you go wide, the things that don't stick too well to yourself. I don't know if that's clear. I mean, it's something that's common in life. Like uh, rehearsing stuff and looking up on the deeper stuff of a specific task lets you go and stick those concepts really really much well than going wider and seeing like a bunch of contexts that they don't have really really kind of a connection or a good basis. So that's why I tend to go deeper instead of wider. So yeah, I mean, it's it's kind of a subjective thing here, but and well, subjective and objective thing, but we have to take the decision and we will see. Okay. And of course, I mean, all this also depends on the project and the time and many stuff that if you have the time and the resources to do this kind of uh, investigation, well, sure, go ahead. But sometimes you don't have that time and resources, and that's why you have to set up a limit on how deep you go on stuff. But since I don't think in the project we have like this kind of strict resource, a strict timing. No, we will see. Okay, so continuing on with this, after the talk, the little talk that we had here, we can see, okay, we have instructions that this is also instruction groups that, okay, we have a table for two that these are recent instructions that have been added to the Intel 64 and i32 processors that basically starts with the SEC 4.1 extensions and two extensions with the CRC RA2 and POPCNT. The A is NEI, PCL move QDQ, AVX, F16C, RDRAN, the sections that follow introduce each subgroup. Okay, so these two are different mnemonics, but they represent the same instruction. So for example, could then the CMOVO and CMOVNO, couldn't those imply the same instruction? No, probably not, because uh, well, no, because they are opposites. Okay. And the party, if I remember, was something about the bits that they were even for some range of bits. I don't remember which ones they were the lowest ones. I remember, but there was some meaning for parity. And there's with if they are even numbers, or not parity if they are odd numbers. There's an exchange. So are these comparing exchanges, are they interlocked ones, or they are not interlocked? Probably not. Okay, so this is interesting. Why does I convert word to double word is the same instruction as converting double words to quad words? Is it because it doesn't matter? I mean, it's probably the same scalar that you use to make that instruction. So it doesn't matter. It doesn't. He doesn't care about the size of the data type, but more about what does it need to perform that instruction. And since he knows that he can convert, he can process words, double words, or quad words inside. Oh Jesus! No. Hold me a second. is so sad. My pen ran off through a hole, and now I cannot find it. But doesn't matter. I will find it later. So yeah, so the thing that I was mentioning was that yeah, for certain expressions, well, for certain instructions, the type doesn't matter at all, you know, or probably for any of them, you know. But of course, if it happens to be on the same, you know, on if it's a general purpose and we're working with IA32 or 64, it can work on it, you know. You can work with a quad word or a double word or a war or a by, or probably by is different. But yeah, you can convert a word to double word or a double word to a quad word with the same instruction. That's nice. But you can convert a by to a word or a word to a double word in EAX register. So probably the CWD, it's a more general instruction that works with words and double words to apply words, and it can be on any register, you know. But if you wanted it to process on EAX, it has to be CBW or the same instruction but different mnemonic CWDE. So probably move SX is with the sign persistent, and move 0 extend it's when the sign doesn't persist and it's set to 0. So it can be this can be useful for casting, for example, or for uh, yeah, when you don't care about the sign at all, you know, or when you care about the sign. Comparison probably, yeah. Okay, so binary arithmetic instructions. Uh, and yeah, I mean, we will need to look at each one specifically and see how can we use them, you know, or we can even make some tests, you know. We have the test for coder test. We have a test CBP there that we can use and write some binary, you know, write some assembly code, you know, so we can test like what's going on, you know. It sounds good to me. The binary arithmetic instructions perform basic binary integer computations on byte and double word integers located in memory and or the general purpose registers. So probably the carry is precisely for that, you know. When you wanna know if uh, sorry, let me charge this and so I can continue. Okay, so yeah. So what I was saying is that yeah, probably for example here the difference with a carry and the overflow is that the usefulness of a carry is that you can know when something overflowed, you know, but you can cache the overflow, you know, or you can cache the data that doesn't or uh, that didn't fit into the register itself, you know. So yeah, I mean the carry. So I mean probably more with it can be for unsigned integers and for signed integers, I believe. And the opposite of carry is with borrow, you know, how much do you borrow from a value, and it's just for subtracts and addings. So okay, with carry and without carry or overflow. My question is, what's the difference between a logical and arithmetic? As logical means like a logical address, or what? And if you see, I mean, there's a difference between shifting to the right, that they are two different instructions, and shifting to the left, that they are the same instructions for logical and arithmetic. So I was looking for SLR because um, I mean, I was like thinking, well, why doesn't it make the mnemonic for shift logical right as SLR instead of HR? And my guess was that there was another instruction that was SLR, but it didn't appear, so I don't know. So SHR shift logical right and SAR shift arithmetic right. SHL same with the other side, and SAL. So I'm curious about. Oh yeah, I remember what was it? Yeah, they just they just scan for a bit set and they return it. They index for it. So yeah. So there's a relationship between the set by the below. I mean, they are the same instruction, but why are they the same instruction? Set by carry, set by the carry. I create. They are here, I guess. Oh, okay, okay. So they set amongst conditions set in the flags register, depending on the state of the selected status flags. Oh, this. Okay, okay. So I would not go ahead in there. I was just like kind of wondering why was that the reason, but it's okay. We will get to there later. And we have, yes, a byte above, not carry if it's below, if it's above, or below if it's carry. So for reading this was that there's a pointer on ECX with an offset of, there's a pointer on ECX that has the base address, and we have SSC4.2 that's a offset, and in that offset we have the CPU ID flag for the CRC32, and the same goes as well for PubCam. Oh, okay, okay, okay. Oh, that's interesting. It's a funny instruction. Calculates the number of bits set to 1 in the second operand, and returns the count in the first operand. That's a cool instruction. Yeah. Okay, okay. But shamefully, it's not, probably not all the target architectures have it. So sorry, probably not all the processors. So that's a shame. Okay. Control transfer instructions. Although I don't know why does they have those instructions all with the byte sets. Does that mean that they are byte sets? Because for being sincere, I understand CRC32. CRC32. So we have a jump if equal, or jump if zero, that's the same. Jump if not equal, jump if not zero. Jump if above, jump if not below or equal. Jump if above or equal, jump if not below. Jump if below, jump if not above or equal, jump below or equal. So there's a special one if ECX is 0, which I remember ECX was for the for a special purpose. I don't think it was a pointer to memory or a string, I don't remember. As a destination. We can take a look, I guess. This is ECX. And it's a counter for string and loop operations. Oh, okay. So yeah, so that makes sense, because if it's equal to 0, you can jump. So it's like a kind of you can use it for loops, if it's 0, for example, if while false or while true or whatever condition there, you can use that instruction to jump the whole while if it's not true. Okay, so I'm not gonna jump, but yeah, so there's some interrupt return function called there's software interrupt on overflow, detect value out of range, high level procedure entry, high level procedure exit. So does that imply that, I mean, we can use move as to move any kind of string type? I guess so. So basically, IO ports work with string data types, which makes sense. So it was CLI, the one that we use, isn't it? No, STI. STI. I don't remember. But STI sets the interrupt flag and CLI clears it. The interrupt flag. Jesus Christ. There are a lot of words with STI. Okay, so these are for the flag control instructions and then the segment register instructions. So that means that they, yeah, I mean they load these bar pointers, and yeah, so the probably, I mean, what happened with 64? Does the, I mean, can we use also the segment register? I think so, but the, yeah, because the base address works as 0. So the effective address, it's also the linear address space. So it will be loaded the same way, I guess. No operation, that's nice. Undefined instruction. There's a table lookup translation. There's a CPU ID, that's the processor identification, which is something that we need to know. We want to know These are the prefetch instructions. There's a prefetch W that basically prefetch all the data into cache in anticipation of writing. Oh, we have already used this one, isn't it? That I want to see if we can take a look at that, because yeah, because we should take a look at that. Let me see. Have this. And as you can see, I've been playing on with forcoder and getting my key bindings to work out, you know. But yeah, I'm still in the process of changing the key bindings. So let me go to this. I will compile. Jesus, this is the longest compilation. Oh my god. Do you see that, man? Do you see that, man? Jesus. Oh my god. Okay. I don't know if we are gonna be able to see it, but I mean, I know that we use that instruction, you know, or at least that's my guess, you know. So let me see if I can. Yeah, where's the flashing instruction? Here's the flashing instruction. There you go, we got it to the flashing instruction. And we go to this assembly. There's a code. Oh no! Oh, oh man, that was crazy. It survived. Oh, thank you, Mr. Visual Studio. I was just gonna say, oh, in the moment of getting out to the point where we know that there's something going on, and Mr. Visual Studio crashes by itself, you know. But it survived. It redeemed himself, you know. Okay, so we are, yeah. This is the instructions that we're gonna do right now. We have already done debug date tracer at and not. It's a jump if not equal, okay. A jump if equal, a test for EAX call, write process memory, and can I have these two things? One by side. There you go. There you go. Let's see. We have write process memory. This one. and that's just happened. We test it against itself, which I don't know why, and we jump if equal. That's because of this, battery to equal 1, and we have this is on the stack, or yeah, it's in the stack, isn't it? Yeah, because this is the function pointer, and there's an offset of blah from the function pointer. I don't know if I can see this. Yeah. Come on, give me the address. Give me that address. Please, the pointer. And this is, well, it doesn't matter. I mean, the point is that, or is this one? Is this one? How can I know? Let me go to memory. And get, I mean, I don't know. Well, probably, I mean, the thing I was guessing is that the 1 was at that part, but it's not. He's just loading 1 and moving it from RAD, that's on 64 register. We're moving 1 to a 64 register, and we have that, and we have our speed is a 64 register. 30. This is a stack pointer. Okay, this is a stack pointer, and we're looking at the stack pointer at 338 hex, and that pointer we are moving it to RDX. Okay, and then a pointer to this state to REX, and then REX plus an offset to RCX. That's gonna be the counter. Do we have a loop there? I don't know. Where am I? Here. Oh my god. Oh my god. Can I see this? Yeah. And this basically has we have a this state, and then I believe the context is on the stack, so it should be dead. 1 is 1, so probably, I mean, it's filling the stuff that, I mean, it's filling the parameters that we're gonna call for flush instruction cache. But I don't know. I mean, I don't see the instruction that I was looking for, that is the flushing, because this is a Win32 procedure. We're not gonna get it, but probably I can go to the call, and I can see flush instruction cache. I just see the definition, well, the declaration. Come on. Well, it doesn't matter. I mean, I was just like kind of intrigued about looking at it. But man, every time, I mean, each time that we read that thing, I mean, it's getting simpler and simpler to understand these things. It's like, hey, I mean, I kind of see the translation from what we're doing uh, on 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 C code or C++ code, and the direct translation to this assembly language. So yeah, yeah. To the disassembly itself. Uh, uh, um, so it's not really difficult at all. I mean, there's a call, it's good, and then there's a move from this state to RAX, that's accumulator, and then hey, we use EAX instead to accumulate RAX plus 44A. That's basically moving an offset from RAX. And then, I mean, this is not super performant, I know, but because we are not compiling with optimizations enable. And this is RCX, it's a counter, and we have that, and then we have a jump basically to the next address. That's gonna be, oh no, because we are in a while loop, isn't it? I don't remember. No, there's a break there. Yeah, this is the jump that we're gonna happen. And then we jump before that. Yeah, this is the first jump for the break. And this is a jump below. Yeah, jump below. This is the first break. This is the compare. Move, increment EAX, move, call, jump not equal. We have an address space here. I don't know if this means that what this means, I mean, this is the address that this offset got, I believe. But it's okay, we can continue. So I mean, it doesn't matter because yeah, surely it's gonna use some kind of that because that flushes and invalidates a memory operand and it's associated cache line from all levels of the processor's cache hierarchy. Now my question is, where does the cache hierarchy it's being explained? Is it explained at all? Or is it just instructions? Because we want to know about the cache itself. Yeah, because I mean, when they say memory, they imply the cache. I mean, that's what it is. But I want to know how does the cache work. Especially for yeah, because this is just the processor, and how does the processor interact with the cache, with the bus and that thing. But there's not too much on that. Probably there's another place where we can look at the cache and how does the cache, how do we operate on the cache itself. Okay, but this is interesting because this manages the cache. We can flush and invalidate memory operand into the cache line from all levels of the processor's cache hierarchy. Okay, flush and invalidates a memory operand associated blah blah cache line from all levels of the processor's cache hierarchy. We optimize memory system throughput. Okay, that's like this kind of big ass member of CL flush optimize. I don't know what extended state save and restore instructions are for, but we will take a look at that later. Save processor extended states with compaction to memory. Okay, so there is a bitwise AND with the first source with the inverted second source operands. I can use bitwise extract lowest set bit, set all lower bits below first set. Okay, that's a good one. That's like lowers mask. And reset the lowest set bit. It's another good one. Zero high bits starting from a specified bit position. Can Okay, so yeah, we have this is instruction that we had to call CPU ID with EAX and ECX and EVX and BMI. I don't remember what BMI was. Oh yeah, BMI was these things, instructions. B3, and there's an offset. Okay, B3, and then bit 8. Okay, so I think we're going to stop right here before going to the x37FB instructions. So yeah, I mean, if you think about it, I mean, they are not a lot of instructions, you know. I mean, they are tiny. They are such a little set of instructions that you can use. I mean, yeah, if you if you look at them as these subgroups, you know. I mean, I thought they were gonna be like huge set of instructions, like this innumerable number that you possibly could not even grasp in your memory, you know. But it's not. I mean, you can understand this. We can understand this. It's simple and it's clear, and that's a good thing, you know. It's not any kind of weird quirky language implementation of a thing, of a kind of expression language thing that is going on. I mean, it's not that. This is the processor executing stuff, and that's it. And I mean, you can read the instructions pretty clearly. I mean, you can see the instructions. You can directly map what the hell is going on here. You know. So what else do you want? What else do you want? The the processor has done pretty much a pretty good job on really being totally explicit of what's going on, you know. And probably, I mean, probably we have, I mean, totally explicit. It's a wrong word, but I mean, yeah, I mean, totally explicit about what's going on with instructions, at least for now. But yeah, okay, so please, if you have any questions, feel free to ask them, and I'll be there to answer them. You can ask them on Twitch or Twitter or YouTube. And yeah, I think that will be all for today. But don't worry, we will continue looking at the IF-82 on the next episode. And it will be great because we're getting to the X87 FPU, which is a lot of fun, you know. So yeah, I think that's all, and I will see you all on the next stream.